I will start. We'll see how far we get.
I'll keep track of time.
So what I'll be walking through here is posted on my web. I mean, I'll try to send you an email with some links to the things I'm talking about at the moment.
Okay.
But basically, I'm going through my I call it Introduction to A-Calculus paper, which was intended essentially as like a primer for my research. And so it's about 50 pages or something, and it is sometimes written in a friendly way, and sometimes I think it's mostly pretty friendly. We'll see. And I will kind of stick to that, but I'll also, kind of let the spirit lead me where we go.
All right.
So just to tell you, like, the basic overall idea of what we're doing is sort of the guiding goal is to understand how calculus works, when we replace real numbers with an algebra. And so the algebra I usually call A, like this, kind of a cursive A. That's my notation for a generic algebra. All right. And so that's kind of the big picture. It's like that's sort of the umbrella in which all the projects I'm looking at come down to one way or another. It's just like, what does calculus look like when you use an algebra instead of real numbers? So in order to appreciate this research, of course, the first thing we need to do is come to terms with what I mean by algebra, right? So what is an algebra? What kind of algebras am I talking about? Now, so I'm talking about, let's see here, if I can find my, so I'm actually now in section 4 of the paper I told you about. I'm not following the paper directly. I think the paper is, I would encourage you to read it as it's written. You will get something out of reading that you're not going to get out of listening to me right now. But anyway, an algebra is, for us, A is finite dimensional real vector space. Paired with a product, which I'll use star for the moment. Star is a mapping from A cross A to A again, so it's a binary operation, right? Such that a couple things hold. Number one, the operation is bilinear. So bilinear means linear in both slots. So that gives us like cx plus y star z is c times x star z plus y star z.
Very scary, isn't it?
I definitely am not leaving right now. And then, wouldn't that be funny if police show up right now and are like, you need to leave? It's like, dude, really? No. I don't think so either. And then, so linear, you have distributive, you break across sums, and you can pull real numbers out both ways. And then this is, right? And this is, of course, for all x, y, z in the algebra and real constants. All right? It's bilinear. I also insist that we focus our attention on associative algebras. So associative, man, x star y star z makes sense. All right, and so, of course, I need to add some parentheses to make that more exciting. And associative. And what else do I assume? I also assume it's a unital. Meaning that there exists, let's say, 1 in the algebra such that 1 a times x equals to x right? So there's a unity, a multiplicative unity in the algebra. All right. Now, furthermore, we say x, an element of A, is an A number. All right. So we think of the elements of the algebra as numbers because, after all, they're generalizing the real numbers. All right. And finally, often, there's a wide swath of my results. Some of the most interesting results, of course, are true in the more narrow context that this multiplication is commutative. All right, so if, x star y is equal to y star x for all x and y in A, then A is a commutative algebra. I'll just say A is commutative. So we're often I find myself working with examples of commutative algebras. There's parts of the theory which I have only worked out in the commutative case. I haven't actually carefully fleshed out how to do the non-commutative case. I mean, it's easy enough to say, oh, it's similar. It's just, you got to keep track of what's on the left and what's on the right. But, there are sometimes some surprises with non-commutative things. And you'll see as we go on, every so often I'll say something like, I think this is true in the non-commutative case. Well, I think this is true, and I've shown it's true, are two somewhat separate things. So if there exist elements such that the product of xy is not equal to the product of yx, then we say it's a non-commutative algebra, right? So
To me, this all just sounds like, how we work in groups.
mm-hmm.
Like we're just working in different groups, essentially.
It is reminiscent of group theory. That is true. But notice that I have not said anything about the existence of like multiplicative inverses.
Yeah.
It's a vector space, right? So it's infinite in terms of cardinality.
Yeah, there's no closure.
Yeah.
But I mean, like the concept of like
Oh,
different
yeah.
groups don't do the same thing.
I think it's helpful to have had abstract algebra as a precursor to seeing this. On the flip side, I think this is helpful as a precursor to abstract algebra. Also, I mean, it goes both ways, the more you know. But, okay, so at this point, I can either start showing you some examples, or I can tell you a few more theoretical definitions. What's your preference?
I have a pretty good understanding of what this is, like relative.
Okay, so let me
Doing the theorems.
let me tell you a few more abstract definitions then. So definition, let's see here. Left multiplication by alpha is a mapping from A to A, and right multiplication by alpha is a mapping from A to A. And so left multiplication is just what it sounds like. So like L alpha of x is alpha star x, and likewise right multiplication by alpha of x is x times alpha. These are the left and right multiplication maps. All right. Now, this is a little slippery. But I mean, don't check this out. So, if we have a mapping, say F from the algebra to the algebra again, has F of x star y is equal to F of x star y for all x and y. This makes F, what I call it, is right a linear. Right a linear. And in contrast, if you have a mapping on the algebra, has, you know, F of x star y is x star F of y, then this makes it left a linear. All right. So like silly theorem, left multiplication, L alpha is right a linear, and R alpha is left a linear. So, like, here's the proof. L alpha of x times y is alpha times x times y. But by associativity, this is alpha star x star y, which is L alpha of x star y. So that shows you that the left multiplication by alpha map is, in fact, a right a linear map. So another just bit of kind of fun associative algebra stuff here is to, just I don't really, it's not super important to my research or anything like that, but it's just kind of a fun comment to make at this point, which is that, L alpha composed with R alpha, well, let me say L alpha composed with R beta equals to R beta composed with L alpha is equivalent to associativity of the algebra. personal, not weather, right?
No, that's what I was checking.
Okay. It's like if there's a tornado on our doorstep, then
Maybe we should stop.
maybe we can get under this table. Oh, we just put the tables on their end and work.
I just go to the bathroom also.
So big window in there, though.
Oh yeah, there is.
I think the smart place to go would be to the mailroom. There's no exterior windows there.
Oh wait, no. Well, what about the auditorium?
Another good example if it was open.
That sucks. Imagine on a tornado. Dude, that's stuck out. But
Yeah. But so like the left and right maps commuting, if you think of what that means, like what does it mean for two maps to be equal? It means that they're equal on all inputs, right? So if you have like L alpha of R beta of X is equal to R beta of L alpha of X, and that's true for L alpha, beta, and X in the algebra, right? Then this becomes alpha star parentheses beta, right multiplication, right, beta star X. And this becomes like right multiplication by beta. So I do this one first, right? I do alpha star X. I can't do math. Right multiplication by, I don't think I can stink. I'm sorry. Let me think for a second. Fine. L alpha, let's see, right multiplication. So that's X times beta, right? R beta, left multiplication, alpha times X. All right, then left multiplication by alpha. And then right multiplication by beta. See, so there you go. The left and right multiplication maps commuting is tantamount to the algebra having associativity. It's like if you want to characterize associativity in terms of mappings, this is how you could do it. You could also characterize it in terms of something called an associator being 0 or something. You can define a commutator as well, and the commutator being 0 is tantamount to the algebra being commutative. The commutator I've shown you before, right? But here, the context like commutator of xy would be x times y minus y times x. All right, so if that's 0, then the algebra is commutative.
okay.
There's a similar thing for associativity that I never write down.
It's the same thing though.
Okay, so anyway, that's just a little bit of these are very special kinds of maps. Not every mapping of an algebra is right or left, alinear. Like these are rather special structures. Like if you took an arbitrary linear map on the algebra, it would not be the case that it's a right alinear map. But these right alinear maps are going to play a special role as we talk about calculus over an algebra. That's why I'm talking about them, okay?
So just because you have something that can commute right does not mean the whole, like everything in the, what do we call these, algebra can commute right. So if everything in the algebra
Mm-hmm.
can commute right,
Yeah.
commute right. Is that what you said? No.
If the product of anything fed into the function allows you to factor the product out of the input to the function like that.
Yeah, then it's right linear. Okay.
Right.
So any arbitrary one.
Yeah, we can.
You can do it for one, but you have
Let
to
me
do it for all.
let me dig into that a little bit more before we go into our examples.
Okay.
Okay, so since it's a finite dimensional algebra, we can make use of a basis. And so I'm going to show you some things about that way of thinking. So if our algebra is, say, the span of, let's say, I'm trying to remember what notation I typically have used in these notes. It's been a minute since I looked at these. So these, so just as a point of personal history, like I started looking at this stuff with students like the summer of 2012.
Okay.
And then like the first full research project arc was 2013. Then it kind of cooled off in some sense. 2014, 2015, I was working with just one student. And that's probably not entirely true, but it just so happens what we worked on went sideways and so we didn't publish anything. But probably mostly my fault. But anyway, that whole process of 2013, 2014, 2015, I was gaining more and more understanding of what we were doing. And then in 2016, I worked with a student over the summer, and in the process of that, I think it was that summer, summer 2016, I can't remember exactly, but I wrote these papers, which were basically just summarizing everything that I'd learned with the students over the past like 4 years before that. And so these things, everything I'm telling you is like, it's something that I have come to an understanding of through synthesis of about a dozen original papers and just working with students. Like some of it's my own. I would say a lot of it is my own. Nothing in here is genuinely new for me, right? It's just using this kind of language to describe this problem is probably, I don't think you'll find other people doing it except for me. I think they should though. Let's see here. I do think I have some original results in this paper, though, I will say that. It is currently unpublished. Oh, okay, so there's my notation. So I'm apparently using V1, V2, Vn, so that my choice of basis is just V's. All right. Then, so we can say Vi star Vj is an element of the algebra, right? So that means that there are constants that we could write it in terms of the basis again, right? And so those constants have a special name. They're called structure constants. So I do C, I, J, and now I got to look at my notation. See, sometimes I write the K upstairs, sometimes I write it downstairs. I don't remember what I did in here.
Oh, this is just a linearity thing, but is that what you're saying?
At the moment, I'm defining structure constants. Just a second, I'm trying to make sure I really should have printed this paper out, but I think you like to have papers on your computer as opposed to, right?
I'm either or.
Either or.
I just can't lose things on my computer.
Okay,
Until this computer. So.
okay, so I use IJ. I use all lowercase. So, it varies. I think I did this to be consistent. Okay, so the two authors which are most close to our approach and really of the same heart for what they're doing for the topic are Ward and Wagner. And these guys were students both of a guy named McDuffie who was at Wyoming, and he wrote a very popular linear algebra book that was used from 1930 to 1950, something like that. But these guys were his students in 1940. I think one of them before Civil War, before World War II, and then the other one, I think they were both before World War II. I can't remember, but The last thing they did was like in the early 50s. And, but they used this CIJK notation. So like I made it, I think my first paper I wrote with the students in like 2013, I had used CIJ and then like an upper K. That was before I was paying a lot of attention to word and vector. We found those after we'd already got the ball rolling. Anyway, I'll stop boring you with history, but I think it's important to know that kind of history so you can, because one of the things that drives me nuts with some people is like I can't tell what they just figured out versus what they know from their education versus what they read in a paper last week, and it's helpful for me to know like what's the tip of the sphere versus whatever. Anyway, so this defines structure constants. One down. So these are the structure constants of the algebra. And obviously, this is very much a basis-dependent idea, right? You have to choose a basis to even do this, all right? In contrast, the definition I erased here was coordinate independent, right? There's no basis in sight. I just told you properties defined. But anyway, the structure constants. And so there are various relations the structure constants have to satisfy because of associativity. If it's commutative, they have to obey certain equations, right? There are equations that you could write for the structure constants, which would encapsulate the things we wrote before. But anyway, that's structure constants. Now, so our
So let me make sure I get this right. This is a C is a vector or vector in relative terms.
C is for a given. If you give me a choice of I, J, and K, C is a number.
Yeah. Oh wait, is it one number or like the?
One number.
Okay.
As
So
the sum is over K, so they're, you know.
Okay, and then EK is just.
That's a vector.
Yeah.
But I mean.
So like we're saying that like.
The vectors are numbers here.
Yeah.
So these are real numbers.
Yeah.
These are numbers in the algebra.
Okay, so if we have a vector k, we can pull out all the constants and say it's still so like 1, 1, 1 and 4, 4, 4 are relatively the same because you can always pull out that 4. Is that what we're saying?
Ooh, I don't know.
If we had a vector in the algebra.
In practice, the structure constants of the algebra, they're typically like 1 or 0.
Okay.
Once we actually get into the examples.
Okay.
One of our customs, in as much as we can, we prefer to set V1 equal to the identity in the algebra. That's not always possible, but when it is possible, it makes results nicest. So if you do that, then, you know, and we identify like 1A how can I say this? Times a constant with a constant times 1A, I should say. And here I do mean dot, I don't mean star, and I'll tell you what I'm trying to get at here. C in the reals. So now this is where it starts to get dicey, but this is also a notation which is typically used. Is C times 1 technically the real numbers? No. But if we're going to think about a number being a real number in disguise, it's the multiples of the identity in the algebra that are those numbers. To really explain that further, I need to start getting. I mean, we'll see that when we get into examples. Okay. Let me just. I'm sorry. I keep punting things to examples. I really need to do examples pretty soon.
Yeah, but the identity can be a vector.
That's right.
So it doesn't always have to be a real number.
Right, but we can think of it as a real number if it's a multiple of 1 because it behaves that way. You know what I mean? Like if I've got a constant times a vector, like scale, this is scalar multiplication, right? That's the same as a constant times 1 in the algebra times x, right?
Yeah.
So I could just as well think of that as the constant times 1a times x by one of the axioms of the algebra. There I'm using like linearity. Well, bilinearity in the first slot, I guess. But so scalar multiplication by c for all practical purposes is the same as multiplication by c times 1a. All right. So now that we know this, all right, let's think about what does the matrix of a linear transformation on A look like with respect to this basis, this customary basis? Okay, so how about, I guess we can use F, right? F mapping from A to A be linear, as in like real vector space, right? And then, so we can calculate the matrix of F with respect to the beta basis. All right? So, as usual, what is that? I told you about that stuff in the course we just got through with here. Let's see here. So
Column vectors of b to n, depending on how many.
oh, see, now I'm starting to dig myself a hole to make this easier to follow in the first pass. I should make an additional assumption about A, which makes it even nicer. Okay. Let's assume that A is in fact as a point set equal to Rn. I haven't really said what A is as a object, except that it's a vector space, right? That could mean all kinds of different things. But suppose it's Rn, all right? And we're going to suppose that E1 is the identity, right? And so, you know, and so forth. This is the usual standard basis, you know. Great. And suppose that we have a mapping F on the algebra, right? Which is right a linear. Let's try to digest that and see what that looks like. So in this case, I really just did what I did just now, so I don't have to talk about the basis. I can just say the standard matrix of F, you know. And we know how to calculate the standard matrix. It's what? It's F of E1, F of E2, F of En. Right? I mean, this is the standard basis of a mapping on Rn. And now here's the sneaky step. Well, E1 is 1, right? But E2, how can we rewrite E2 in terms of E1 here?
We just did it. 1 times the identity times anything.
Mm-hmm.
Try it that way.
Right. Right, so we could say E2 is equal to E1 times E2, right?
What is BF?
E2 is E1 times E2, right? And so forth. So let's do that here. We've got f of E1, f of E1 times E2, f of En, E1 times En, right? But we're assuming what? That the mapping is right alinear, right? So that means that I can rewrite this as like f of E1 times f of E1 times E2, f of En, or rather f of E1 times En. So the standard matrix of a right alinear map, if we're using the basis, all right, where the, E1 is the identity, multiplicative identity for the algebra, then the first column completely fixes what happens to the rest of the columns. Like all you have to do is know the first column, and then you multiply by E2 to get the second column, multiply by E3 to get the third column, multiply by En to get the nth column. So this is very special, right? Like most matrices that appear as linear maps of a vector space are not going to have this pattern. You're like, well, you haven't really even told me one algebra example yet, so I can't quite understand what pattern you're getting at, but I guess I'll have to trust you. So I think at this point, to flesh out everything I've told you so far, we need to start looking at examples, right? Okay, so I guess I should mention definition. I think I call this if I think I say that the matrix representation of V is equal to V times E2, V times En. So this is an element of Rn by n. Well, I see curses, my notation. MA. So this is an element of what I call MA, all right? That is itself a subspace of n by n matrices. And matrices like this are sometimes called the regular representation of A. So we can in fact prove this set of such matrices is isomorphic to the algebra itself. All right. And in fact, when we dig into it, it's more than that. The mapping M, it actually preserves multiplication in a certain sense. Multiplication in the algebra ends up being encoded as multiplication of matrices in M sub A. I have theorems about this. Okay, I'm getting distracted from my examples though. I just want to introduce that notation so I can show you some regular representations of our examples as we're going on. That's all. Okay. So number one is a very boring example. A equals to R itself. So this is an algebra. All right. And, you know, connected with our original goal, this makes sense, right? We're trying to generalize calculus over the reals. If we're going to say something about calculus over an algebra, it had better make sense when we make the algebra equal to the reals. Otherwise, what are we generalizing, you know? In this case, you know, x times y is it's just equal to xy. So we use juxtaposition for the product. We don't really need the product. And in here, there is just v1, which is equal to 1, you know. So like 1 in the algebra is the number 1. And the structure constants, what are they? 1, 1, 1 is 1. It's very... this structure constant being 1, that is a sneaky way of saying 1 times 1 is equal to 1. That's what that means. All right, 2. A equal to the complex numbers. And I'll think of the complex numbers as R2 for the moment, in the sense that it's A comma B, such that A and B are reals, right? And A comma B star C comma D is AC minus BD comma AD plus BC. Now, of course, like this is not our usual notation for complex numbers, right? Notice that this is equivalent to like A plus BI, right? C plus DI, how's that work?
Complex.
Right, AC plus I squared times BD, right? Plus I times B, well, AD plus BC if you work it out. And of course, I squared is what?
-1.
-1, right? And so this definition of star up here is the complex numbers. Defining the complex number systems on R2 in terms of like a formal multiplication like that, that's been done since like Gauss's time. I forget who. Some people will say it's Cauchy, other people are like, no, it's Arg. I don't know. I lose track of who's supposed to get credit. I don't much care, honestly. Sorry. It's so hard to say who did what first in the 19th century, honestly. Like, I just... Okay, so now that can I erase the multiplication?
Where?
Just this?
Yeah, let me just get this last bit. Okay. Yeah, you're all good.
All right. So really, an alternative way of defining that is you could have just said that, like, you know, I times I is -1 and then proceed normally. You know, in other words, this is A plus IB such that A, B are real, and I squared is equal to -1. Right? And then just say something like proceed normally. This is often how it's done in like engineering courses. You know, the usual multiplication and distribution laws hold, just with the extra caveat that I squared is -1, right? So that kind of formal approach is bothersome if you don't believe in the existence of complex numbers, right? Well, everyone believes in the existence of pairs of real numbers, And if you accept that my previous definition is the complex number system, then you have a concrete model of it, right? It's the R2 with that multiplication I just erased. All right, so getting back to my basis stuff. So here we have V1 is equal to the number 1, which in terms of vectors is 1, 0 here, right? Which, full disclosure, is a column vector, 1, 0. You know, my usual notation, all right? And what's V2? V2 is I, which is, well, 0, 1, which is my sneaky notation for 0, 1, right? So just, a little bit more on structure constants. And I'm not trying to draw too much of your attention to structure constants. I really do try to avoid arguments with structure constants as much as I can, but maybe this is useful. I times I is the sum over k equals 1 to 2 of C2 to k. V k. Which here would be like C221 V1 plus C222 V2, right? But what is this? So apparently, we know that this is equal to minus 1, right? Which is, in our current notation, minus V1, right? So you can see from this that apparently the structure constants are C221 is equal to minus 1, and C222 is what? Is there any complex coefficient here? Like the multiplication of I times I is pure real, right? There's no complex piece. So C222 is in fact 0. Right. So, I mean, if you have an example where you have the algebra, the rule for the multiplication defined, it's a simple matter to go through basis by basis and figure out what the structure constants are. It's just kind of tedious and not particularly interesting, but you can do it. And in fact, if you go back and look at Ward and Wagner, those papers I was talking about from like the 30s to the 50s, they're obsessed over the structure constants. Everything for them is structure constants all around. And basically what they explain in there, among other things, is that you can use the structure constants to find the regular representation. Essentially, whether you fix the first or the last or the middle indice will either give you the left, the right, or something else representation-wise. But I feel like I'm getting way, way into the weeds there. I'm just throwing that out there. Now, let's take a look at a linear map on R2, right? And see what it means for it to be right complex linear. So what's that mean? Let's see here. How about this? We have f from the complexes to the complexes, right? And let's see here. How about we have f of x plus iy equal to 3x minus y plus I times 4x plus 7y, right? You can verify that that is in fact a linear map by any variety of arguments, but one of the simplest and laziest ways to do that is just to rewrite it in column notation. Right, remember, because 1 is the vector 1, 0 here, but I is the vector 0, 1 here. So as a two component vector, that's what this complex number is. And then of course you can just, okay, well that's 3 minus 1, 4, and 7. XY, right? So is this a right linear map? Right? So to answer that, we need to first answer the question, what does an arbitrary right linear map look like for the complex numbers, right? So
wouldn't it be something that's like f of x or x plus f I y under star or multiplication?
You have to have what?
Going back to the definition, the x plus f I y.
Uh-huh.
Would that not be?
Well, yeah, well, to appreciate the right linearity, we have to have f of, x plus iy times, like, I don't know, a plus ib is equal to f of x plus iy times a plus ib. Now here, you notice I'm not writing star anymore because we have juxtaposition as our star. And that has to be true for, this has to be true for all x plus iy and a plus ib in the complex for it to be right linear, right? But we have a theorem, right?
Yeah.
I mean, you could just use this to figure it out. That's true. But our theorem that we have is that if f is right alinear, then the matrix the matrix of f is an element of this guy. And in fact, this is not just an if-then. You can make this a if and only if, because I proved the forward implication of this over here with this calculation. And this is context here. I'm assuming, for brevity of discussion at the moment, that A is equal to Rn. These things, that's not the thing in the way of this generalizing. It's just that by assuming that the algebra is Rn, we're suppressing a basis dependence to our arguments. In my paper that I was talking about, the Introduction to Calculus, I have all the gory, tedious basis dependent versions of these theorems are all there. But if the algebra is Rn, f is right alinear, and of course I'm assuming f is a mapping from the algebra to the algebra, right? That's the context here. Then f is right alinear if and only if the standard matrix of the map is in MA. To be in MA means that the matrix has the form that the first column generates everything beyond the first column by multiplication in the algebra. This is the definition of MA right here.
Oh, yeah. E1.
So to prove the other direction, like that if it has that form, then it's right linear, I mean, we could prove that, but just take my word for it at the moment. Maybe we can prove that next, okay? Notice here what that means then. So we have to have the matrix of f has the form like f of E1, right? And then f of E1 times E2, right? In our current context, that's what this means, right? Because there's just two dimensions, and so if we make the first column a plus ib, the second column has to be a plus ib times I. Right?
Yeah, but you get a negative, which would be
So a plus ib we write as the column ab, right?
Yeah.
A plus ib times I is ai minus b. Minus b goes up here because it's the first one, and ai puts a down here. So this right here is what the regular representation of the complex numbers look like. It's 2 by 2 matrices of this form.
Okay.
Geometrically, they're rotation reflections, rotation dilations. So I can say with confidence, no, this mapping is not right complex linear because it does not have the right pattern. These have to be equal. These have to be off, but the same, but off by a sign.
Yeah.
It just isn't. As I was warning, write a linearity of a linear transformation on algebra is a super special, like, you know, what's the dimension of all linear transformations on an n-dimensional space?
What's the dimension? Oh, n. Wouldn't it be n?
Nope. Like, if you look at the set of all linear transformations, say from R2 to R3, you can prove that there's a bijection between that space and the space of matrices that are 2 by 3. So it's actually 2 times 3. It's 6-dimensional. If we're looking at linear transformations from an n-dimensional real vector space to an n-dimensional real vector space, the space of it's n by n matrices. It's n squared dimensional.
Yeah.
So this MA is a n-dimensional subspace of an n squared dimensional real space.
Okay.
That's, you know, so these are rather special matrices in the world of all possible matrices. And they're also, in this other sense, very boring because they're not invertible. Like, check this out. This means that it's got rank 1, I'm pretty sure. Well, I could be wrong about that. I think I'm wrong about that.
Yeah, well,
I'm wrong about that.
It can't be invertible. It's just
I'm a dummy.
kind of by ejection, right?
I'm a dummy. Is this invertible? I mean, often. This is, in fact, this is almost always invertible.
Yeah.
Okay, so real numbers, complex numbers. Next example. Unless you want me to prove the converse.
No, that's good.
Okay. That would be a good exercise for you to work through, actually. So example 3, I call H. This is the x plus jy such that x and y are real numbers, and j squared is equal to 1. Now, if you doubt the existence of such a formal system, it's a relatively simple matter to define H as R2 as a point set. Like, I could just say, we could think about H equal to R2, right? And here the multiplication would be xy times ab is by definition xa plus yb, comma, xb plus ya. Like, that defines the multiplication on R2. In particular, 1, 0 times 1, 0. So 1, 0 times 1, 0, if you look at here, what happens? So x equals to 1, y equals to 0, a equals to 1, b equals to 0. If you look at this definition, you just got 1, 0 again. You tell me what happens for the other one, the 0, 1 times 0, 1.
1, 0, 1, 0, 0, 1, 0, 1. That has 1, 0. The y, b would be 1, 1. No. XA is...
A is 0, so xa is 0.
And then y would be 0, that means b would be 1?
Well, so 0 for the first component, right? Oh, so
Oh, the bottom term, sorry.
yeah, we got y equals 1, b equals 1. Oh, wait a minute. Y and b are both, I'm an idiot. Y and b are both 1, so I'm sorry, it should have been 1. Dummy.